Thank you. So we are now coming to lecture number 47, continuing our discussion on modeling, most models. So the last lecture, we were talking about the linear region current relationship in the language of SPICE. We have also written the expression of VTH, again in the language of refining another parameter VTO. And now we have seen the third xj1 is a parameter which has, instead of writing L effective, which is not a SPICE parameter, we are writing L minus 2xj1. xj1 is a lateral diffusion, is a SPICE parameter. In the saturation region, level 1 continued. In the saturation region, for which you remember the VGS must be always more than VTH, otherwise device will not conduct. However, VDS now is more than VGS minus VTH, so that the saturation occurs, but this is not a perfect saturation. So as before, already we have brought in lambda to explain, to account for the channel length modulation effect. That will also naturally contain in the saturation region also. This is given by Kp by 2 W by So this is the equation for the current in the saturation region, which we got from this by substituting VGS minus VTH. VDS is equal to VGS minus VTH. So if I do not consider the second term, this is a square law relationship, a power equation, and you remember it is independent of VDS, perfect saturation. However, due to the channel length modulation effect, we have incorporated this multiplier 1 plus lambda VDS. Lambda is called the channel length modulation parameter, which is one of the SPICE parameters. If I review, then I find that we have the following parameters: Kp, that is equal to mu Cox dashed. We have a parameter gamma, which is a body effect parameter, which is twice epsilon s q na. You'll find actually in SPICE it is written Nb for the body, but because it is Nb is Na for NMOS and Nd for PMOS. Please remember this, which I forgot to tell you. And twice 5p is the same old thing we have already discussed. And Cox then we have to introduce lambda, xj1, L, etc., which are all SPICE parameters. L is the gate length, mask gate length, xj1 is the lateral diffusion, lambda is the channel length modulation parameter, and the remaining things are as follows. Then typical electrical parameter values may be like this. Say Kp is equal to 27.6. I am giving some textbook. VTO These electrical parameters and the physical parameter values in the old days of technology was like this. I told you that these are the values in the old days of technology. How do I say that? All these values are valid for 70s or in the beginning 70s, in fact entire 70s and maybe up to 81, 82 maximum, not beyond that. Things change very rapidly. By seeing which data you can say that these are values for the old days of technology. What is the value of TOX? 100 nanometer, that is 1000 angstrom. It is the oldest, 1000 angstrom to 1200 angstrom typically was the gate oxide thickness in the very old days. Another thing you note that mu, though in bulk silicon, mu n is about 1400 centimeters square per volt second. Here mu has been taken to be 800 centimeters square. It is surface mobility. But this is also quite small because the oxidation techniques, surface roughness, silicon surface preparation, etc. were not that much perfect. The scattering at the interface was more, leading to a lower effective mobility. Then you see the value of xg1. That clearly states the value chosen. That clearly states is real, definitely an old technology. Can you tell me why? Already I have indicated that. Now why 0.8 micron? They have suddenly 0.8 micron. Hmm? Scale perhaps was taken to be 10 micron. I am not remember here. Yeah, you're right. But actually, in the old days of technology, initially it was aluminum gate. Okay, aluminum gate. That diffusion. It was a pure alignment. Aluminum, there is no scope of any self alignment. Do you understand by self alignment? I discussed earlier. If I normally, if it is an aluminum gate technology, what has to be done? You have to first define source and drain, grow the gate oxide, deposit aluminum, pattern the aluminum to form the gate. Okay? While patterning aluminum to form the gate, what are you doing? How can I align the edges of the aluminum gate with respect to the edges of the diffusion at the source end and the junction edges at the source end and the drain end? How can you do that? That has to be done by simple alignment technique. Is a mechanical the mask aligner which is used for this purpose. There are precise movement technique, that is the micro positioners on the stage through micrometer controls. But because it is mechanical in nature, you could not ensure a very high order of alignment of the edges of the aluminum gates with respect to the source boundary, the junction boundary and the drain junction boundary. What was usually done? Suppose I plan for 5 micron gate length. 5 micron suppose is my effective channel length. L effective is 5 micron. Between the source and drain is 5 micron. That is defined by one mask. The source and drain diffusions were done using one mask, and there we have already defined some distance. So when I do the diffusion, I finally know what is the value of L effective. And then suppose L effective is 5 micron, it typically we used to keep L means this one, which I have already defined, the length, this one, which is defined during the patterning of aluminum, which is about 1.5 times or sometimes double the value of LF, so that I get always an overlap this side and that side. It cannot be exactly the same. If it is 5 micron, we may get about 2 micron overlap here, 3 micron overlap here, or 1 micron overlap here, 1.5, depending on the accuracy of a mask alignment, because we are not using any self-aligning technique in the initial days. So xj1, xj2, I could have easily define. So xj1, practically speaking, is the average of the xj1s of the two sides in the early days of technology. But then polysilicon gate technology came. What was that process then? You first define a source and drain, grow gate oxide, channel implantation concept came later, okay? But then it was used, but in the initial stage, PMOS, initial stage was all PMOS technology, let me tell you. But then this thing was like this. You grow thin oxide, deposit polysilicon, patterned polysilicon, of smaller, the actual polysilicon you are making, say, this much length, okay? Then polysilicon, through using polysilicon as a mask, you now diffuse phosphorus. So what will happen? Yeah. In fact, in that case, what people were doing, this initial diffusion, source drain diffusion could be done later, not initially. You have a very thin oxide, gate oxide, define polysilicon, deposit polysilicon, define polysilicon gate of length L, then remove the oxide, okay, and diffuse for phosphorus or boron, depending on the technology. So initially you do pre-deposition and then you do some drive-in. So what will happen? Polysilicon will diffuse, the impurities will diffuse in this direction as well as in this direction. And typically I said for diffusion case, lateral penetration is around 80%. So it was very typical that the junction depth was 1 micron, the xj was 1 micron, and xj1 was 0.8 micron, because it is 80% of that. That is the philosophy. So these values clearly indicate that it's a very old technology. And then the values of QP, which is mu into COX, VTO is assumed to be 1 volt, gamma is this much, etc. They are dependent on these values themselves. Using these values, you can do yourself. You can generate the curves. Because L is suppose 10 micron or 5 micron. You are after, it came when implantation techniques. Initial implantation means aluminum gate, but then implantation was done. But gradually aluminum gate problem is it could not resist, once you deposit aluminum, you cannot go to high temperature. And secondly, aluminum cannot be oxidized. Polysilicon technology was so developed, LPCVD technique, ultimately it was found that polysilicon is the most suitable gate material, standard today. So many things happened together. As a result, things started changing. Now, using therefore these values or any typical values, and using these equations, you can write down. I will request you to do so. You just write a small computer program for level 1. All of you, I request you to develop a computer program for level 1, where the parameter values I have mentioned, we take and compute the IV characteristics for any choice of the parameter values. But you have to do it nicely. So that will give you some training in software development. In the sense that you'll be using SPICE, this is something, but if you want to develop the SPICE, or if you want to develop a simple circuit simulator, what you have to do, you have to just write the program in a slightly commercial fashion. I will say that you have an input file and right, and maybe some little bit interactive mode you can give, and so that at any stage you can see and modify and check and see. And here what you can do, you can just generate the IV characteristics under different conditions. Some of the things which has been done, let me mention here. For example, I am taking from some calculations straightforward from the level 1. Level 1 is not that accurate but very educative, no doubt of it. Zero, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 in microampere. This is the characteristic called transfer characteristics. Transfer characteristics of a MOSFET, where value of VDS, I don't remember, maybe a very small value, maybe a 1 volt. Linear region. So ID versus VGS, and maybe L was 10 micron. You can do your calculation yourself. I told you that these are typical values. It shows a very sharp threshold because it is a linear plot. Linear plot. ID is a linear scale. VGS is also a linear scale, and you find that ID stops flowing at 1 volt, indicating that VTO, this is VBS is equal to 0. So VTO is 1 volt, which is the case considered here. VTO is 1 volt. But then with a minus 5 volt reverse bias at the body, at the substrate, the curve shifts and the voltage becomes around, VTO becomes, not VTO, the VTH becomes roughly around 5 volt, around about 2 volt, 1.9 volt kind of voltage. The effect of Kp is also seen here. Higher is the Kp value. Kp can be influenced by mobility as well as by thickness of the oxide or COX. Okay. So increasing mobility, a small rise of mobility shows the nature of the curve, the sloping. You know that. What does it say? Delta ID by delta VGS for a constant VDS is GM, transconductance. Delta ID is for the same value of delta VG, delta Ig is more for the second curve, is expected because mobility is more here. So whatever you have got, there is nothing, but you can generate such curves. Let us see the curve which is generated for the output characteristics. This is called transfer characteristics. So you generate the beautiful characteristics of the MOSFET so easily using the equations, rather simple equations. And you get the dependence of these curves on various factors. So for example, as you see here, Kp has been used as a factor. You can use gamma as a factor, phi p as a factor, NP, Na as a factor. So many other parameters can be used. So you can generate this curve for small shifts of the different, the substrate concentration is a little bit adjusted. VBS is adjusted. I have not here, I have assumed VBS is equal to 0. Here, for all these curves, VBS has been taken to be 0. Okay, but we could do it for different VBS, etc. The equations are simple, but very, very productive, I should say. The equation level 1 is simple, it's rather simple, but it gives you a lot. And you will find the difference between the experimental data and your curves. There will be good amount of difference, but can be absorbed to a great extent, seeing the qualitative nature of the curve. So far as the qualitative variations are concerned, everything agrees with the experimental things. So I will request you to please, once again I will request you to please develop a simple program, write a simple program for analyzing the current voltage for the NMOS. You write it in such a way that it is applicable for NMOS, PMOS, and you can combine the two to have a CMOS joint characteristic. That means if you consider a CMOS, PMOS, NMOS in series, how to get the voltage current characteristics or output voltage, input voltage characteristics, inverter. If you are smart enough, you can develop all of them. You first develop the simple thing, but you can combine them to have a simple circuit simulator for the inverter, NMOS inverter, PMOS inverter, CMOS inverter. Everything is possible. There is nothing new. Let us now go to, so this is the level 1, the simplest in the MOSFET modeling. Okay. Then came level 2. And that was due to Meyer. A little bit later. Let me tell you, the level 2 is far superior to level 1. It is based on physical models. Empirical things are to a great extent removed. As a result, level 2 predicts the experimental data much more precisely than level 1. However, level 2 is very complex. People who are circuit simulator people, SPICE people, they did not like it. That's why next came level 3, which was very much acceptable by the SPICE people. Let us discuss level 2. Level 2, everything you have done earlier. This considers drain induced depletion. Which was ignored in the level 1. Level 1 ignored drain induced depletion, and level 2, then the current equations etc. were derived earlier. I just to remind you, remember that the charge stored in a layer of thickness dx in the depletion layer. Large charge stored in a layer of thickness dx in the depletion layer is now written as this plus Vcx is the addition. This is the channel. I think we wrote as simple Vx in our analysis earlier. Remember, I gave you two derivations of the current voltage equation of MOSFETs. First one was simple, which ignored the drain induced depletion, but the second one considered the drain induced, and that was more complicated. But I told earlier that is more accurate than the first one. Where you remember the depletion, also the square root of this, which comes along with the depletion layer with the expression, isn't it? Square root of twice epsilon s into twice phi p plus Vp. I was writing plus Vs divided by QNA. That is the depletion layer weight. So to calculate the charge, naturally the square root of this thing was coming in gamma. It has now been gamma has now been brought out, means that twice epsilon s, QNA, etc. has been brought outside through the term gamma in our SPICE equation. Here we have now added that Vcx. Vcx is the potential voltage at the surface due to the current flow, due to the ohmic drop called channel potential. And that I also told that is also taking part in depleting the channel. I told earlier that channel cannot be depleted beyond phi s is equal to twice phi f. That is so far as gate induced voltage is concerned. But when there is a drain induced thing, current is flowing due to the voltage applied in the drain. As a result, there is a potential drop across the channel. That is in addition to phi s. And as a result, there is further, that is why the depletion layer gradually widens towards the drain from the source. Okay, considering that, and that's how ultimately, you remember, I derived an equation which is far more complicated than the first model, looking like this. I would request you to please compare this with your previously developed equations. Three by two. This equation was derived in the class earlier, so I am not re-deriving it. Compare it with this equation for the level 1, which ignores the drain induced depletion. Just compare the two. Compare. You just look at this equation for level 1 and look at this equation for level 2. You find here, is there any gamma related term? Gamma, which is dependent on Na, epsilon s, etc. It does not appear in the level 1. You see, in level 2, the gamma term has appeared. That is a clear distinction between level 1 and level 2 equations. So, IDS depends on the gamma also. And here, in level 2 derivation, we assume that for VDS is equal to VD set, what we assume? We assume that QI, the inversion layer transiency at L dash, the point of pin-off, it may be L effective also, is equal to VGS minus VD set minus VFB. These things are all done earlier. Plus, please note that the symbols have been now changed. This was my presumption. I said that Qi at the drain end should be 0 at pinch off. That means at the onset of saturation. That's how saturation voltage was defined here as compared to the first case. In the first case, the saturation voltage was defined as, in the first case, you remember the saturation voltage was defined as this one. And VD sat is equal to VGS minus VT. Straightforward. VD sat is simply equal to VGS. But here VD sat is to be derived by solving this equation. VGS minus VD sat minus VAB CO dash minus this is equal to 0. By solving this equation only, you have to find out. And this VD sat will be slightly different from the VD set which I have observed earlier. I have already made such remarks earlier that the VD set to be obtained by solving this equation which is slightly different, but definitely it will be more precise. That is why, that is a clear distinction, and this is very important. And therefore, okay, I'll be coming to that next. So please remember, that is how you have to find out the value of VD set. To be obtained this can be done analytically, unnecessarily you can do it, but you can write a small program to do it. It is up to you. Then, so far as implementations is concerned, we write VTO in level 2. I am continuing level 2. In level 2, so far as implementations are concerned, VTO is expressed as phi ms minus q ns s cux dashed right, and TPG So you see that here actually VTO has been physically modeled Just instead of giving the value of VTO, which was the case earlier, you can now calculate VTO using a more physical model where phi ms has been written like this. Instead of QF, they prefer to use QF by Q, which is called NSS, the surface state density. But this is so far as the non-stoichiometric layer is called fixed oxide charge. There is a fast state, that is a different thing. And this term TPG has been brought in the equation for phi ms, whose values are three discrete values: 0 for metal gate, -1 for polysilicon gate doped with the same type of impurity as a substrate. If substrate is p-type, say in MOS, substrate is p-type, then the polysilicon gate is a p plus polysilicon gate. This is valid for p plus polysilicon gate. And this is for n plus polysilicon gate. Can you justify why it is like this? They have not suddenly written this equation. This is analytical equation. This is not an empirical equation. Can you justify why it looks like this? How they derived it? What is the basic assumption made? The basic assumption is that they have assumed that for the metal gate, particularly aluminum gate, the value of phi m, the metal work function, is the same as, you can note down, value of phi m, the metal work function. They have assumed that phi m for metal, particularly aluminum gate, they write metal but they mean aluminum, let me tell you, otherwise it cannot be 0, for your information. Metal but aluminum in their mind, metal gate, they have assumed that phi m is approximately equal to, what is chi, this one? This is electron affinity of the semiconductor. The distance of separation, energy separation between the vacuum level and the conduction bandage. These two are roughly equal. One is 4.1, the other is 4.15. In practice, they are equal. If that is so, do you justify that TPG is 0 for metal gate? I will request you to verify it. TPG is 0 for metal gate, that means then this term is absent, on phi ms is simply given by this equation. And otherwise, some minus or plus, for example, for except for NMOS, with p-type silicon substrate, if the polysilicon gate is a p plus polysilicon gate, you have to write plus Eg by 2 minus this to get phi ms. If it is n plus polysilicon, which is usually the case for NMOS usually the gate is n plus. So in that case, what is the value of phi ms? Is minus TPG minus Eg by 2, because it is plus, minus Eg by 2 minus this thing. So this has to be kept in mind. So this is so far as the VTO model is concerned. And in linear region, as before, which is defined as before, VGS is greater than VTH and VDS is greater than, not greater than, VDS is less than VDSAT. VDSAT has to be obtained by solving that equation. So I am not giving you a simple formula for VDSAT, but VDSAT has to be obtained by solving that equation. In that case, IDS in the language of SPICE is written like this, KP. You just see some changes. Don't comment now. You see that here, if you leave aside this numerator 1 minus lambda VDS, it is the same equation as the one which I have written here. Beta has been transformed, so it is the same equation written here. You can easily see. And however, this term, which was earlier written as a multiplier in level 1, it was whole thing multiplied 1 plus lambda VDS. But now, instead of that, they have preferred to write in the denominator 1 minus lambda VDS. What is the significance of this 1 minus lambda VDS here? Again, let me tell you, this is an empirical kind of thing, but there is some more physical thought behind it rather than pure empirical thinking. This 1 minus lambda VDS, in fact, in the linear region, they have conceived it as an effect of drain-induced barrier lowering. Drain-induced barrier lowering. Because in the linear region, when VDS is small, why at all this thing should come? That means there is a little bend and end bias may have a small effect. In addition to the channel length modulation, in addition to that, there will be some effect on the drain-induced barrier lowering, which is reflected this equation. So this 1 minus lambda VDS takes into account both, that is drain-induced barrier lowering and definitely the channel length modulation, which is reflected, which is felt also in the linear region. And in saturation region, where VGS is definitely VTH more than and VDS, they model IDS as ID set into another thing that is an interesting thing. This is an interesting question. You see that they model in the saturation the drain current as this. ID sat is that point, that it is the current when VD is equal to VD sat. Okay? That you calculate from this formula, putting VDS is equal to VD sat value, which you have obtained by solving that equation. QI is equal to 0 equation. Okay? And then what you do, you now insert a second multiplier, 1 minus 1 minus 1 upon 1 minus lambda VDS. So here you see that there was originally in this equation was 1 minus lambda VDS was there. A second term has come in, and they have found that, you know, this is all based on experience with while fitting with experimental data. Experience with while fitting with with experimental data, they found the modeling the current equation in the it can push these devices in the micron region. Otherwise, if I do not consider this equation is more or less okay for around up to 3 micron or 4 micron, but below 3-4 micron, if you want to validate the model, they found that putting this in as a multiplier becomes more this thing.